In this video, we're going to talk about what it means for a sequence to converge in a topological space. So here's our definition. If x tau is a topological space and xn is a sequence of points in X, then that sequence converges to a point X in X if for each open set U containing the point X, there is a positive integer n such that little n greater than n implies that x sub n is an element of U. So that's saying that we've got our point X, and we're saying no matter what open set we choose around X, there is some n in the natural numbers such that n larger than that value implies x sub n is an element of that open set. So eventually there are all these points x sub n in this open set U. In this case, we say that x is the limit of the sequence x sub n. So let's compare this with our previous definition in a metric space. So we said that in a metric space xd, the sequence xn converges to x if for any epsilon greater than 0, there is some natural number n such that n greater than that value implies the distance between xn and x is less than epsilon. So we're saying that here we've got our point x. We can pick any epsilon greater than 0, epsilon, and for that value, there is some n in the natural numbers such that n greater than n implies that the distance between xn and x is less than epsilon. This is equivalent to saying that the ball centered at x of radius epsilon contains xn. So then all our xn's are in that epsilon ball after a certain point. So we see that this is definitely a similar idea, especially when we think of this distance between points in a metric space being the same thing as being inside a ball of radius epsilon, which again looks kind of like this open set U sort of idea. So if we're talking about x tau, if x tau happens to be the topological space generated by some metric on the set X, so that is the open sets or the elements of the topology tau are unions of open balls b sub d x r, balls of radius r centered at x for this metric d, then it is the case that convergence in the metric space implies convergence in the topological space. So that is, let's say that we've got some sequence xn that converges to x in the metric space, and that tau is the topology on X generated by D, this metric. Then if we've got some open set U and some X inside of it, because U is open in that metric space, that means that U is a union of open balls. That means there is some epsilon greater than 0 such that the ball centered at X of radius epsilon is contained inside of U. And so therefore, since xn converges to x and epsilon is greater than 0, there is some n such that for all integers greater than it, the distance between xn and x is less than epsilon. In other words, we're in that epsilon ball. That epsilon ball is contained inside of U. So for n greater than this point n, the point xn, the elements of the sequence are elements of the open set U. So yes, if tau is generated by a metric D, then converging in the metric space implies converging in the topological space. So we know that every metric space is also a topological space. So again, just by tau is just the open sets in XD, and open sets in XD are unions of open balls, unions of balls centered at points X of varying radiuses. But is it also the case that every topological space is a metric space? So We don't really know the answer to this yet, but we're about to. So here are two theorems about convergence in metric spaces. So the first, if we have a metric space, then a sequence cannot converge to more than one limit. So in other words, it can't be that xn converges to x and xn converges to y, where x is not equal to y. This is not possible in a metric space. And that definitely makes sense why that's not possible. If x and y are not equal, then that means that the distance between x and y is greater than 0. Say the distance between x and y is equal to, let's use epsilon. Then we've got our point x, we've got our point y, and we could think of balls of radius epsilon over 2, and the definition of convergence would say that xn has to be inside this ball for all n greater than some value, and also in this ball for every n greater than some value. These balls are disjoint, and so we've got a contradiction. So this is a theorem we already talked about previously for metric spaces. Something strange, we're going to show that this is not true in a topological space. This theorem is not true for topological spaces in general. Secondly, if A is a subset of a metric space, then a point X is a limit point of A if and only if there's a sequence of distinct points in A that converges to X. We also showed this previously when we talked about metric spaces. And again, we're going to show that this theorem also is not true for metric spaces. So we're going to show that in both cases. For each of these theorems, this is generally that are always true about metric spaces. We're going to show that it is not always true in topological spaces. So in order to find a counterexample to theorem 3.8, we want to find a counterexample for topological spaces to theorem 3.8, that a sequence cannot converge to more than one limit. Let's look at the real numbers with the finite complement topology. So the finite complement topology is the set of open sets, or the sets in that topology are the empty set, as well as any subset of R whose complement is finite. So this is the finite complement topology. Now consider the sequence 1 over n equals 1 through infinity in this topological space. We know that in a metric space, if R with the usual metric, of course this would converge to 0. We're going to show that this converges to pi in the finite complement topology. In fact, this sequence can converge to any real number, and of course that will be a counterexample to the idea that a sequence cannot converge to more than one limit. So this is true in a metric space, but not true in a topological space, and this counterexample will show it for us. I'd like you to start to think about why that's true. So, in thinking about why that's true, what's the definition of convergence in a topological space? To show that this sequence converges to pi, we need to show that for any open set containing pi, there is some number n such that for values greater than that number, 1 over n, x sub n, is an element of the open set containing pi. So that's what we need to show. So pause and think about that, and we'll talk about it together in a minute. Okay, so we've got the real numbers with the finite complement topology. Let's let U be an open set containing pi. Now U is open, so therefore U either has to be the empty set, can't be the empty set because it contains something, so it has to fit the other criteria. U is a set such that its complement is finite. So since U is an element of this finite complement topology, and U is not the empty set, that means that U complement the cardinality of U complement is finite. So there are finitely many terms in U complement. Then that's the case that for some n in the natural numbers, 1 over n is not an element of U complement for n greater than n. If this was not the case, then U complement would not be finite. So there must be some point at which 1 over n is not an element of U complement. And therefore, that means that for n greater than n, 1 over n is therefore in the set U. So we do have that for n greater than n, 1 over n is an element of U, and this tells us then that therefore the sequence 1 over n converges to pi. Now there was nothing special about pi. It was just some element of the real numbers, and we just said U is some open set containing that point. Similarly, the sequence 1 over n converges to x for every x in the real numbers with the finite complement topology, this very special topology. So we've shown not only that a sequence can converge to more than one point, a sequence can converge to infinitely many points. So we see that a sequence can converge to infinitely many distinct or different points in a topological space, which is weird, certainly. Again, it is a counterexample to this theorem about metric spaces. So this theorem does not hold for topological spaces. The other theorem that we said was true in a metric space but does not generally hold for a metric space is that a point is a limit point of a set if and only if there's a sequence of distinct points in that set converging to the point. In other words, this connection between limit points of a set and the limit of a sequence. So again, we're going to show that this is not generally true through a counterexample. So let's consider the set X consisting just of 2 points with the trivial or indiscrete topology. So that is, the only 2 open sets are the empty set and the entire set. In that case, what are the limit points of the set containing just B? What are its limit points? And remember, in a topological space, point X is a limit point of a set if every open set U containing that point contains some point of A other than X itself. So pause and think about that for a moment, and we'll talk about it together. Okay, so we've got our set, X equals AB. What are the limit points of the set B? So is A limit point of B, or the set containing B, in this topological space? Well, the only open set containing A is the set X. So X equals A comma B is the only open set containing A, and this open set contains some point B other than A that is in the set B. So B is in the intersection of X minus the point A, and it's in the set containing B. So therefore, yes, A is a limit point of the set containing just B. However, B is not a limit point of the set containing just B because we see that, the only open set containing A or containing B, X minus B intersected with the set B is empty. So we see that B is not a limit point of the set containing B. Okay, what were we trying to find a counterexample to? We were trying to find a counterexample to X is a limit point of A if and only if there's a sequence of distinct points in A that converges to X. So we see that A is a limit point of the set containing just B. Is there a sequence of distinct points such that the sequence X sub n converges to A? Well, the key word here is distinct. Distinct means different, right? There are only 2 points in this topological space. No, there are only 2 points in this topological space, and therefore there is no infinite sequence of distinct points of this, converging to anything. There just cannot be any infinite sequence of distinct points. And so definitely there's no infinite sequence of distinct points converging to the point A. So we see that the forwards direction here is false for a topological space, for topological spaces. The other direction, however, is true. This other direction is true for a topological space. So if it is the case that you have an infinite sequence or a sequence of distinct points, we're assuming infinite, that converges to a point X, then it will also be the case that that point to which the sequence of points in A converges is a limit point of A. So you will show that this is true in the homework. But this if and only if of this original theorem is false for topological spaces. So what we see is that there are theorems that are true about metric spaces but false about topological spaces. What does that tell us? This tells us that there are topological spaces that are not metric spaces. That is, there is no metric that gives these topological spaces. So, we're talking about R with the finite complement topology, for example, or this set X equals AB with the indiscrete topology empty set X. We see that these are both what we call not metrizable. These are not metrizable topological spaces. There is no metric that on either of these sets that is equivalent to those topological spaces. So that big question, we know that every metric space is also a topological space. Is the reverse true? Our answer now is no. There are topological spaces that are not metric spaces. There are topological spaces that cannot be given by any metric on that set.